Okay, we are now on our last section about the hypothesis testing and the last section about chi-squared test for hypothesis testing. We're looking at chi-squared test for association. So that's whether two traits or characteristics in a population are somehow associated. So again, well, the scenario has to satisfy the properties of a multinomial experiment, um, which means there's got to be a fixed number of independent trials. The outcome of each trial can be classified into exactly one of several categories, and the probabilities for the different categories remain constant for each trial. Um, so the variables don't have to be numerical, and the relationship doesn't necessarily need to be linear. For example, we can look at whether there's a relationship between gender and choice of car color. Um, what we do use are the frequencies for every possible outcome, which are going to be numerical. Uh, Sample data has to be randomly selected, and again, as we saw with the previous section, the expected frequency for each possible outcome has to be at least 5. Okay, the 4 steps for hypothesis testing still don't change. State the null and alternative hypothesis, determine which distribution to use for the test statistic, and state the level of significance, gather the data, and calculate anything you need to, and draw your conclusion and interpret it. Okay, so the null and alternative hypothesis for this, as the last time, are fairly simple. Um, Null hypothesis, the two variables are independent, right? In the gender and car color example, um, car color and gender are not related in any way. Um, the alternative or test hypothesis is that the variables are not independent. Gender has some impact on preferred car color. Okay, so it ruins their examples. Um, for the gender and car color example, we've got gender and car color are independent for the null hypothesis, and gender and car color are not independent for the alternative hypothesis. State the distribution to use and the level of significance. All right, so if we plan on randomly selecting 1,000 cars and recording the gender of the car owners and the color of their cars, um, assuming the other conditions, multinomial experiment, etc., are met, we can use the chi-square test statistic. In this case, we are going to use 0.01, so 1% for this test. If we gather our data and calculate the necessary statistics, so there's we can summarize our data in what they call a contingency table. There's our random sample of 1,000 cars. In this contingency table, we've got male, silver cars, black cars, red cars, and other. Apparently not many blue or green cars uh, in this example. Silver, black, red, and other. So we've got 575 males, 305 total silver cars. Um, so there's the values for each individual one. 190 males who own silver cars. The sum, so this should be it. This row is also the total number of males we talked to. Um, sum in this column is the total number of silver cars. In a contingency table, the expected value of a frequency can be found using this little formula. Take the row total times the column total and divide by the sample size. So in this example, if I'm looking at an expected value for males owning silver cars, I'd have 575 as my row total times 305 as my column total divided by my 1,000 sample size. Silver cars owned by men. So 575 was my row total, 305 was my column total, 1,000, I just showed you that on the table. There we go. So that's my expected value should be 175.375. So we would continue and do that for each cell in the table. So it could make a contingency table of expected values then. So there'd be my expected value that we just calculated, a corresponding one for female silver car owners, etc. Just double checking because these numbers were looking very familiar on the other one, and it looks like yes, it looks like the sums in each column and row are unchanged. I don't know if that's a property of contingency tables offhand or not. I expect it might be. So now we've got the expected values. We can calculate our test statistic. We're going to use the same formula as last time, which is the observed frequency minus the expected frequency. Take that difference squared and divide it by the expected frequency and sum those up for each possible outcome to get the chi-squared statistic. So we would have, right, so this is our male silver car owners, 190 minus 175.375 that we calculated. This would be the same value for the female silver car owners. That's the expected frequency from the table. Do that for each value, so there should be 10 values. There were 10 values in that table. 1, 2, 3, 4, 5, 6, 7, 8. Silver, black, red, other. Okay, 8 values. Sorry, my mistake. So we get 30.805. So we need to know the degrees of freedom so we can find the critical chi-squared value to compare against. With association, this is determined by the number of rows and columns in the contingency table. So we do this with rows minus 1 times columns minus 1. In this case, we've got 2 rows minus 1 would be 1 times 4 columns minus 1 would be 3. So we have 3 degrees of freedom. Okay. So we'll use the critical values for the chi-squared distribution. And if our test statistic is as large or larger than what we calculate is as large or larger than the critical value, we can reject the null hypothesis. So we've got a significance level of 0.01. We've got 3 degrees of freedom. Just need to look up x squared 0.01. Okay, there we go, 0.01, 3 degrees of freedom, 11.345. Okay, so if we're greater than 11.345, we can reject the null hypothesis. We calculated 30.805, so we reject the null hypothesis and the evidence that gender and car color are not independent. We can say gender and car color are related, and this affects what other statistics we can do sometimes. There's a lot of assumptions that variables are independent when you're doing some sort of study. So that they're related means that further analysis needs different things. It needs different examination. Okay, so let's look at some political data. If this was information collected during the 2008 presidential campaign, surveying 13,660 random voters. So there's male voters, female voters, Democrat candidate, Republican candidate, other candidate. There's our observed contingency table. Is there evidence at the 5% level to say that gender and voting choice were related for this election? Okay. So, state the null and alternative hypothesis. Null hypothesis would be that gender and voting preference are independent, and so the alternative hypothesis would be that they're not independent. Okay. Which distribution to use and the level of significance? We're looking for association. We're told that in this chapter, at least, we can always assume the necessary conditions for this section. You know, in reality, that would be something that we would need to test, but we're not going to get into how to test for that, so we're just going to assume it for now. So we'll use the chi-squared test statistic. We were told the level of significance we were after was 5%, 0.05. So let's gather and calculate the necessary statistics. So we need to first start by creating an expected value contingency table, right? So that's row total times column total over sample size. Row total, column total, sample size. Row total, column total, sample size. It's repeated each time. So we come up with these expected values. And now we can calculate the chi-squared statistic. Again, we've got the observed value minus the expected value. Square that difference divided by the expected value. And we do that again for each cell in that table. And we get a 67.276. Okay, so first we need degrees of freedom. We had 2 rows, and 3 columns. So we've got 2 degrees of freedom and a 5% significance level, alpha 0.05. We find the critical value is 5.991. Our calculated value is much greater than 5.991, so we must reject the null hypothesis. So at the 95% confidence level or 5% significance level, we can conclude that gender and voting choice were related for the 2008 election. Note that this is for the 2008 election only. We can't necessarily generalize this to all elections. We can't generalize it to say which way the any specific gender leaned. It's just that there is a relationship for that election. Anything beyond that needs further analysis. We can also do this on a calculator. So we're looking at a relationship between hair color and combination of gender and marital status. Get a random sample of clients, and we get the following data: single women, single men, married men. So we've got four rows, 4 columns. We want to know if there's evidence at the 0.1 level of significance to say there's a relationship between a person's hair color and the combination of gender and marital status for this hairdresser's clients. So this is, again, specific for this hairdresser's clients. So we're going to use the calculator here. Again, have to do the first couple steps by hand. Null hypothesis would be that these variables are independent. The alternative hypothesis that we're researching, the research hypothesis, is that they are not independent. Again, we're going to assume that all the necessary criteria is met, so we can use the chi-squared test statistic, and we're after a 10% significance level, which would be a 90% confidence level, so 0.1 and corresponding 0.9. Okay, data have been gathered and presented as a contingency table. When we're using the calculator for this, we do not need to calculate the expected values like we would by hand. Um, we start by inputting these as a matrix. We give it the number of rows and number of columns, so it's 4 by 4. Input our data. Tell what we want to do a chi-squared test. Give it the matrix we want. It will calculate the expected values and store them for us as B. And then it will calculate our chi-squared value and the p-value associated with that. So we can, at this point, just look at that p-value and say that is greater than the 0.1 significance level, so we cannot reject the null hypothesis, because we can only reject the null hypothesis if the p-value is less than the significance level. It will also calculate the degrees of freedom for us based on that. So, right, degrees of freedom in this case is rows minus 1 times columns minus 1. So 4 minus 1 times 4 minus 1 is going to be 3 times 3, or 9. Right. After the test is run, we can go in and look at the expected value matrix. So again, our conclusion, since the p-value is greater than alpha, we fail to reject the null hypothesis, and there's not enough evidence at the 10% significance level to conclude an association between gender and marital status, between hair color and a combination of gender and marital status. So that is it for hypothesis testing and chi-squared distributions. Hopefully it makes sense. Please be sure to bring questions to class if you have them, and I will see you soon.